Hello student, very good morning to all of you. I hope you all are happy, healthy and fine at home. What were we discussing yesterday, or what did we discuss yesterday? Yesterday we have discussed about the general summary, whatever we have learned about that according to the syllabus, point number B. So that summarize collectively in that, and there we have seen what are the basic thing required for next point for the synthesis of the following molecule, or the molecules are these. And what we are going to learn today is we are arriving at the last stage of this Chiron approach. So far we have seen A point is the introduction, B point is that utilization of that basic concept, where what is that chiral template, chirons, and what kind of the carbon framework. So how to apply that carbohydrate type symmetry, because some of the natural product there is, we can see apparent carbohydrate type of the symmetry are present there. In some of the natural product, partially hidden carbohydrate type symmetry is present, and in some cases, in some of the natural product, there is a hidden carbohydrate type of the symmetry are present. But how to arrive, how to approach that Chiron approach, and how to arrive up to that all the basic thing we have learned so far. So today we are going to start. This is a very important as far as your exam point of view is concerned. This third point is a very important, the utilization of basic concept for a retrosynthetic strategies in the synthesis of these are the 6 molecules, and that 6 molecules are the very important one. Yes, propanediol. Number 2 is R and S epichlorohydrin. Third one is L plus alanine. Fourth one is minus multistatin. Fifth one is minus pentenomycin, and sixth one is a Sikhimic acid. These are the 6 molecules. We are going to see their retrosynthesis as well as their actual synthesis. What are the mechanism behind it, how to arrive that one, all these basic concepts we have seen so far. But while using this, while synthesizing this, we are keeping in mind the Chiron approach. We should not go away from that Chiron approach. Your starting material or the chiral precursor, how it is easily available, or the availability and the cost. According to that, all the stereochemical aspect, stereo selections, or stereo electronic control or steric control, everything we are going to keep in mind. So yesterday we have learned how the Chiron approach retrosynthetic advantages over the retrosynthetic advantages, how they are greater with the certain point we have explained or we have studied yesterday. And today we are going to see some of the already we have discussed that one. Let us quickly revise. Those are the terms generally use, common terms generally used in the retrosynthetic analysis are as well as while the retrosynthesis by keeping the Chiron approach, there are also some of the common points we are using. So let us begin with the first one is the target molecule, and as we know that this is called as a TM or the target molecule. What does it mean? Target molecule means what? Target molecule means the molecule whose synthesis being planned is called as a target molecule. In general retrosynthesis analysis also, but here the target molecule, in this by applying as a Chiron approach, we are going to see there are the 6 target molecules are here. One is a S-propanediol, second one is a RS epichlorohydrin, third one is a alanine, fourth one is a multistatin, fifth one is a pentenomycin, and sixth one is a Sikhimic acid. These are the target molecule. Specifically we are going to study these 6. They are the target molecule, or they are the target means whose target molecule means what? Whose synthesis being planned is known as a target molecule. Generally here using as a retrosynthetic strategy, we are going to apply what will be the perspective. Perspective should be the Chiron. Your starting compound must be the chiral precursor, and that chiral precursor must be easily available. The cost everything is very low, cheaply available, pure, and that are the precursor we are going to use for the actual synthesis of this compound. And there we Chiron also. Chiron is one of the word. It is made up of by the two term. One is what is that? Chiral, and second word is what is that? Synthon. And as we know that in the retrosynthesis also, yesterday we have seen some of the terminologies they are used in the retrosynthetic analysis. So retrosynthesis means what actually? Retrosynthesis means what? An imaginary but logical reverse chemical reaction which help us to reach the reactant starting from the target molecule is known as retrosynthesis. Understood this one? Retrosynthesis means what? An imaginary. It is a imaginary but logical. There should be logic behind it. Otherwise you cannot do randomly, you cannot break the bond randomly, you cannot go the breaking of that molecule randomly. So there should be a specific imaginary but logical reverse. This is a reverse reaction than the forward, and therefore we have reverse chemical reaction. An imaginary but logical reverse chemical reaction which help us to reach the reactant or the substrate, or what we can call it as a chiral precursor or the template is known as a retrosynthesis. An imaginary but logical reverse chemical reaction which helps to reach the reactant starting from the target molecule. Specifically here are the 6 molecules that are known as retrosynthesis. This is the word generally we are using here as well as in the general sense. Retrosynthetic analysis, here we are keeping the Chiron approach or the Chiron perspective for the synthesis of this target molecule. And just now we have seen target molecule means what? The molecule whose synthesis being planned is called as a target molecule. Now let us see as another one term. While planning the scheme, there must be some analysis are there. So by keeping in a mind, we are breaking that molecules or we are converting into some other molecule. So this molecule could be made from this one. So that type of the thing. So that is analysis are there, and that term is generally used there. The term is known as a retrosynthetic analysis. That is a retrosynthetic analysis. While keeping as a Chiron approach, how do we do that? Retrosynthetic analysis. Retrosynthetic analysis is nothing but it is a process, one of the process. The process of breaking down the target molecule into convenient starting material using disconnection and FGI is known as a retrosynthetic analysis. FGI means functional group interconversion. Means the process of breaking down the target molecule into convenient starting material using disconnection. Disconnection, it is one of the important step used in a retrosynthetic analysis, and another term again is a functional group interconversion, and by using this term is known as a retrosynthetic analysis. Again I am repeating here, retrosynthetic analysis means what? The process of breaking down the target molecule into convenient starting material using disconnection and FGI is known as a retrosynthetic analysis. It is a very important step in a retrosynthetic analysis, or in a while in half part, because if suppose is a 4-mark question may appear in your exam, so half mark means 2 mark for retrosynthetic analysis and half of the part that is for the actual synthesis. How you can synthesize this compound by using as a various reagent, proper reagent and the reaction condition, how you can synthesize this actual, because you already have that target molecule, but by starting with that precursor, that is a template, how you can make that molecule by using the proper reagent and the making the suitable or keeping the suitable reaction condition, so that you can arrive, you can reach to the target molecule. So that is called as a synthesis is here, right? So these are the some of the terminologies we are generally using while in the retrosynthetic analysis or in a because this approach, that retrosynthetic strategy we are going to use over here, and that's why there is a need to remember some of the term, what are the term are involved while synthesizing some of the target molecule. And I think third one is known as a just now we already seen as a first one is a retrosynthesis, second one is a what we can call it as a retrosynthetic analysis, then target molecule. Now is a disconnection, and disconnection is an important step in a retrosynthetic analysis as well as in the Chiron approach also. That term is a disconnection, and that disconnection is should be disconnect the molecule in such a way that you should get the proper segment, or the what we can call it as a Chiron, and that Chiron should have symmetry or chiral center, sense of chirality, stereochemical aspect, everything must be there in that Chiron. So that type of the thing you are doing, that is called as a disconnection. Disconnection, it is an analytical operation. Disconnection, an analytical operation which break a bond and convert a molecule into a possible starting material is known as a disconnection. Disconnection, remember disconnection means what? An analytical operation which break a bond and convert a molecule into a possible starting material. Starting material means template here or the precursor, that is known as a disconnection. And it is an analytical operation. We are by keeping the reaction while disconnecting the bond, before that you must know, you must have the name, you must have a systematic or the name reaction to form that carbon-carbon new bond. Then and then that way you have to disconnect. So that's why it is a very, very important step involved in a retrosynthetic analysis. That is an analytical operation which break a bond and convert a molecule into a possible starting material, or what we can call it the template or the precursor, is known as a disconnection. And then we are using as a synthon in general statement. Synthon means what? Synthon is nothing but as they are associated with the polarities. And in a general retrosynthetic analysis, we take as any target molecules are there, you break it. After breaking the bond, we are getting plus and the minus charges. That type of the fragmentation, one should have a positive, another should have a negative. So that type of the fragmentation are known as a synthon. And another terminology, another important term using in a retrosynthetic analysis, what is that? That is a synthetic equivalent. Synthetic equivalent means what? Synthetic equivalent, again the synthetic equivalent means what? The reagent carrying out the function of synthon is called as a synthetic equivalent, because that positive charge or that negative whatever fragment you are getting, that should they are the highly reactive in nature, so it should have a synthetic equivalent. And synthetic equivalent is nothing but as the reagent carrying out the function of synthon is known as a synthetic equivalent. This is a term generally we are using in a general retrosynthetic analysis. Another term we are using in the retrosynthetic analysis, what is that? Reagent. And reagent, you are hearing, you are familiar with this word from your 12th standard. Reagent, do you can you define reagent? What does it mean? Reagent is nothing but as a compound which react to give an intermediate in the planned synthesis or target molecule itself is known as retrosynthetic, is known as reagent. Suppose as a sodium hydroxide or potassium hydroxide, sometimes is a H2SO4 or HBr. These are the reagent we are using. What does it mean? Reagent, because at the reaction site these reagents are attacking, they bring the chemical changes, and one of the functional group is converted into as another. So that changes are occur due to the reagent, and that's why that reagent bringing the chemical changes, that is called as a reagent. Means the compound react to give an intermediate in the planned synthesis or target molecule itself is known as a reagent. And the last word is a FGI. FGI is the full form of FGI is a functional group interconversion. It is also one of the important term used in the retrosynthetic analysis, in a general retrosynthetic analysis, as well as in the while applying as a Chiron approach or that Chiron perspective. So that is a FGI. So what does it mean? The FGI, full form of FGI is a functional group interconversion. And FGI, the one of the functional group is converted into another functional group, so that disconnection becomes possible, is known as functional group interconversion. FGI, functional group interconversion. Go on interchanging the functional group until you have in your mind, you can make that bond, you can convert that functional group by knowing the named reaction, so that type of the thing is called as a functional group. Interconversion, one of the functional group is converted into as another functional group, so that disconnection becomes possible, is known as a functional group interconversion. These are the basic requirement or the synthetic these word we are frequently going to use while synthesizing these. There are the 6 molecules are there, they are the target molecule. I already told you that the target molecule means what? The molecule whose synthesis being planned is known as a target molecule. Let us see here first the structure of that 6 molecules. One by one we will see the structure, because we must be familiar with this structure, and then we can do the retrosynthetic analysis, and the synthesis is very just one. In a retrosynthetic analysis we are going backward, reverse chemical reaction, and synthesis means forward reaction. We are going to start from the substrate or the starting material, here specifically as a chiral precursor, and we are going to synthesize the molecule, that is which is actually these are the target molecule. Let us see here S propanol, and as we know that these S are here, you will find here are S. So these are the term why they are used. These are nothing but as a absolute configuration, because stereochemistry playing very excellent role, very significant role in the stereochemistry, because they exhibit the R configuration, exhibit different chemical properties as well as physical property, and S configuration also exhibit, because the drugs and whatever drugs are the medicinal compound, they should be very highly pure in nature, pure, then we can apply, otherwise there is a adverse effect on the mankind, or what we can call it on a human being, and that's why these compounds should be, while synthesizing in the laboratory, very high precautions are taken while synthesizing these, because if the one of the molecule, whether suppose, let us see another example, as everybody familiar with that paracetamol, where it is used for decreasing what we can call it as a fever. So that type of the compound should be highly pure in form. So let us see the structure of S propanediol, and just now I told you that S means it is a absolute configuration, and where in the carbohydrate chemistry or in alpha amino acid, there we are using as a capital D and the capital L. They are the relative configuration, and these R and S are the absolute configuration, whereas sometime is used as a small l and small d, or instead of small d or a small l, sometime it is shown here like this, plus or minus. A plus is nothing but as a dextrorotatory, minus means it is a levorotatory, and levorotatory means rotate the plane of the polarization through left hand side. And as we know that these compound are the, when they are in a optically active in nature, then and then they can rotate. And optical activity, it is one of the important property of the organic compound, physical property, and the instrument used to determine the optical activity is a polarimeter. And as we know that optical activity or the optical isomerism means what? The certain substance rotate the plane of polarization through a certain angle is known as a optical rotation or the optical activity. Now let us see here these. And now remember that capital D and capital L don't consider with that plus and minus. These are the experimental quantity, and that are the relative configuration. Your capital D may have a plus or minus, or your capital L may show that is a what we can call it as a plus or minus, means small d or small l. So don't get mix these two terms, they are totally different. So let us see the propene diol. Look at here, propane. So propane diol, sorry, here is a propane diol. Diol means, as we know that while we already learned the while doing the protection, deprotection, adjacent means vicinal dihydroxy compound is known as a diol. So this type of the things are the diol, OH and the OH, that is 1, 2, 3 and 4. This is called as a vicinal diol, and that is called as a propene diol. The structure of propene diol will be this one. Here is a CS3 group, and now I am showing here this is a OH first structure, and this is also as a OH. Look at, this is a structure of what we can call it propene diol. Why can you tell me how many chiral centers are there? And as you might be knowing, at chiral center, chiral means what? The carbon atom carries 4 different groups are known as a chiral carbon or the asymmetric carbon atom. Look at, in this molecule there are only one chiral center is present. Here, look at here, this is a carbon atom and it is shown by the arteries or the star is a chiral center. If you look at here, and as we know that chiral, there is a one rule is there, that rule is known as a CIP, or you can call it as a sequence rule, right? Sequence rule, CIP rule or sequence rule. Sequence rule, CIP means Kahn, Ingold, Prelog. They are the scientist name. They have given certain rules are there. There are 5 rules are there. The sequence rule means what? The arrangement of group around the chiral center is known as a sequence rule. There are the priority number. The arrangement of priority number around the chiral center is known as a sequence rule, and rule number 1 is called as a atomic number. Those atom, because 4 different group, those atom or group having as a highest atomic number, it should get the first priority, and then second priority, third priority, and the fourth priorities are there. Likewise, you can give the priorities over there. But in the second rule is suppose both 2 groups are having connected with that carbon, then go for the next atom, and this is the second rule. Third one is a double bond or the triple bond, because that group may contain the carbon multiple bond or carbon nitrogen multiple bond or nitro group, that type of the things are there, or carbonyl group. So this double bond or the triple bond. And fourth one is a isotope. Isotope you might be knowing. Isotope means what? Isotope, suppose in case of the hydrogen atoms are there. Hydrogen atom has a 3 isotope. Which are those? One is a hydrogen, second one is a deuterium, third one is a tritonium. All are having their atomic number are same, 1, 1, 1, but their mass number are different. Hydrogen has a 1 mass number, deuterium has a 2, tritium has a 3. So like that. So according to that, now look at here, by using that rule, look at here, oxygen, here is a, imagine here is a hydrogen atom over there, here is a hydrogen atom, this is a chiral center, only one chiral center is present in this propene diol, the OH, they are adjacent to they are relative position of these 2 hydroxy group. These hydroxy group bearing with that carbon atom 1 and 2, that's why it is called as a diol. 2 hydroxy groups are there and therefore it is a diol. If you give the number according to the atomic number, it will be the first. Then now look at here, Here one rule we have applied here. Now look at here carbon. Here also as a, imagine here is a CH2, right? Here as a carbon atom, here also as a carbon atom. This carbon atom further attached to 3 hydrogen atom, H is you can write here, and this carbon atom further attached to oxygen atom and 2 hydrogen atoms are there. So now tell me which one is a bigger one. This should becomes as a bigger one, therefore it will get the second priority, and now this methyl group will get as a third priority. And as we know how to travel from 1 to 3 always go like this. What type of the rotation it is? It is a clockwise manner, and therefore it should be as a R. But look at the fourth priority group at a horizontal, then that configuration should be invert. So it will invert means it has a S configuration, and this has a S configuration. In this way you can remember why this is a S propane diol. So yeah, why it is given as a S propane diol, this is a configuration in this. Now this is a first one. Second structure, let us see. Second structure is a R and S, epichlorohydrin. Epichlorohydrin, do you know the structure of epichlorohydrin? You are not knowing till now. Let us see here. Epichlorohydrin has a structure is a this one. Let us see here. This is a structure of epichlorohydrin. This is a structure. This is a type of a epoxide type of the structures are there, and this what will be how many, if you look at this structure, if you observe this structure carefully, now can you tell me how many chiral center are present here? Is there chiral center is present or not in epichlorohydrin? This is a structure of epichlorohydrin. Is there chiral center present in this molecule? Yes or no? Yes, there is a one chiral center is present. If you look at here, this is a CH2 group, right? Here is a CH2 group. Here only one hydrogen atom is there, and here is a CH2. Means there is a epoxide type of the species. Here it has a one chiral center. Remember, only one chiral center is there. In this first case also one chiral center is here. Here also has a one chiral center. Now what will be, whether it has R configuration or S configuration? What do you think? This again apply the sequence rule. By using that sequence rule we can easily find out this one. Suppose oxygen atom, this group is oxygen, let us see, this will get the first priority, right? Now here this CH2 and this CH2, now this carbon atom further attached to here oxygen and 2 hydrogen atom, right? And now this carbon atom has one chlorine atom and 2 hydrogen atoms are there, right? Now which one is has a bigger, in case which one has the bigger in nature, bigger, whether it is a R configuration or the S configuration? Look at here, oxygen having as a atomic number is a 8, but chlorine having as a 35, and therefore it should be a second priority number, and this one should be as a third one. Look at this one, go for 1 2 2 3. So what type of the rotation it is? You can see this is a rotation like as a S rotation, right? And now look at this hydrogen atom which is present horizontally, and therefore we can change invert it configuration, it should be the R configuration, right? This is the R configuration. And now put the mirror here. Just you keep, as we know that this is a mirror. What do you see in mirror? They are the mirror images, means mirror image, enantiomer. Have you heard this word? Enantiomer means what? Non-superimposable mirror images are known as a enantiomer. And exactly you draw the structure here. This mirror image you can see here chlorine, and this should get as a R changes to into S, and therefore it is known as a R and S configuration. That is the structure of epichlorohydrin. Understood this one? Now let us see the structure of L plus alanine. Alanine, this is one of the alpha amino acid. Structure of alpha amino acid is a, as we know that this is the third one. Let us see the structure of that one, third one, the structure of alanine. So this is a, what we can call it as the amino acid, and this, and while writing this amino acid, the most oxidizable group should be written on the top, and here is a yellowish shown, means that amino alpha amino acid means that amino group should be or must be on a left hand side. Here H, and here is a CH3 group. This is the structure of L plus alanine. That is a plus, that is the experimental quantity we can decide here, but L we can say because that NH2 group we on the left hand side, and that's why it is a L configuration. This is a structure of L alanine, H2N H. And how many chiral center do you see here? There are only one chiral centers are there, right? Chiral center, and by using that you can easily find out the configuration or S configuration. So generally naturally occurring amino acid L configuration should have the S configuration. If you find out there 1, 2, 3, you will get as a S configuration over there. Look at here. Suppose it is look at this chiral center, carbon, carbon, nitrogen. Nitrogen has a 1 priority number. Among these, this is a carbon atom, this is a carbon atom, right? Both are having apply the second rule. This carbon atom and this is also as a carbon atom. But again apply the third rule, because carbon oxygen generally we are writing as a this carboxylic group is a this manner, C double bond OH, means this double bond is nothing but as a COO, means here you can write O and O, 3 oxygen atoms are added over here, and here is a H and H. So ultimately this is a second one, this should be the third one. If you go from 1 to 2 to 3, what do you see? This is the R configuration. Again hydrogen atom present at a horizontal, and therefore it will give the S configuration, and means all naturally occurring alpha amino acids are having S configuration. So that you can keep in mind. The next one, so fourth one, that is a structure of pentamycin. Fifth one is the structure of pentamycin. Pentenomycin, structure of minus pentenomycin is again penta indicate, a pentene indicate as a 5-membered ring, and that 5-membered ring has this type of the compounds over there. Pentamycin, structure of that pentamycin will be this one. Here is a hydroxy group, I am showing OH. Here again as a hydroxy group, hydroxy group, and another one is above the plate, and there will be the OH, right? So this is a structure of minus pentenomycin. I think we have forgotten fourth one is a fourth one. Here the fourth one structure is a multistatin. Multistatin, the structure of multistatin is like this. You can show the structure of multistatin is this one, this type of the structure of this multistatin. So this is a structure of minus multistatin. One ethyl group here, another ethyl group, and as we know that in the chair form, the group which are at equatorial position are more stable in nature. So that type of the structure is called as a multistatin. And the last structure is a Sikhimic acid. the structure of Sikhimic acid is this one. This is the structure I am showing over here. Sikhimic acid is there, and therefore there should be as a acid group COOH, C double bond OH, that acidic group, and then at this position one of the OH group is above the plane, another OH group below the plane, another OH group it is also below the plane. This is the structure number 6, and this structure we can show like this. The structure will be on like as a, by using as a Haworth formula we can use this type of the structure. We can draw here. Here is a double bond, then there should be C double bond OH, then here you can write this OH. Now at this sum there are 3 I think we are missing something. Let us see, draw properly this one. The structure of this one is not, because in the ring there is no oxygen atom here. Let me change my let us see here. This is a structure of what is a, here we can put as a double bond here, and here is a carboxylic group COOH, carboxylic group in this case, and next one will be what is a, there is a 3 hydroxy groups are there. One hydroxy group is above the plane, one hydroxy group is above the plane, and 2 are below the plane. So we can show these are below the plane, this is also as a below the plane. So these are the 6 structure, and the general introduction we have seen here. I think tomorrow we will start the next one, actual synthesis of S-propanediol. Till then, so we are going let us stop today here. Thank you. Have a nice day.